So today's lecture, this is lecture 7 on the plasma membrane. Um, we've started already with an introduction about what's in this plasma membrane. We talked about phospholipids a lot. We've talked about cholesterol. We've also talked about how we regulate this plasma membrane, this cell membrane, right? We talked about the fact that sometimes fluidity can change if you have different types of phospholipids, if you have cholesterol in the membrane, all right? But now I really want us to get to the meat of what this cell membrane is used for, right? It's used as a barrier to let certain things in and out. So we need to talk about membrane transport and how things are moving across the membrane or if they're getting stopped, right? And this chart here is very nice at summarizing all the types of transport in kind of one little picture. So take a look at this if ever you get a bit lost. Now, before starting, um, this slide is not in the slide deck, but I want to remind you about a few terms that we've seen in the past, or maybe you've talked about at some point. I'll be using these a lot: solute, solvent, and solution, right? A solute, right, is kind of like the physical thing that you're putting in, right? This could be salt that you're putting in water. So the salt would be the solute. It's the actual kind of substance, right? That maybe it's ions, maybe it's proteins, right? But it's some kind of it's not the liquid that you're putting it in, it's this solidish stuff. And the solvent, right? There's a V in it, like volume. So this is like the volume of water, right? Solvent is like whatever you're mixing this substance inside, right? So here I'm mixing salt and water. Water is the liquidy kind of stuff that I'm putting the salt in. Think of it like the salt in a soup, you have the solvent, which is your broth, right? And all the little vegetables and other stuff, right? This is the solute that you're putting into the solvent. And so when you mix these two things together, we create a solution, right? So your soup with the vegetables and the broth would be considered the solution altogether, right? So a solute plus a solvent will form a solution, and our whole bodies are solutions, right? Humans are made out of water. We are a lot of water is made out of makes us up, right? And things are dissolved in us, right? All of our blood, right, is practically water with a few things inside of it. So this blood, this solvent, right, is water in our blood, and we mix a bunch of proteins and even ions like salts, right, that are mixed in this blood. We have different enzymes. We have um, glucose that's mixed in this watery blood, right? So all of that together forms a solution in our body. So I'm going to be using these words a lot, right? And I want us to know them a little bit. So the specific composition of the cell membrane will influence its fluidity. We saw this before, right? Like what molecules are made up over here will influence how fluid, how loosey goosey things could enter or exit the cell, right? If we had those phospholipids that had those tails that were a bit bent, then things could get through easily. Um, how is fluidity related to the membrane's function? Why did we talk about that before? Because fluidity affects how easily certain solutes can get through. Look over here, right? Certain solutes are passing through the membrane directly, right? If it's very rigid, then maybe they won't be able to do that. Some of them pass through these membrane proteins, right? So fluidity could affect the amount of these membrane proteins that are there. So, you know, the entering and exiting from the cell really depends on this fluidity of this membrane, right? Here's our intracellular environment inside the cell, and here is the extracellular environment outside the cell. And we get things in and out from here, right? Now, this is what we talk about when we talk about, you know, allowing things to come in or not. We say that the cell membrane is a selective barrier, okay? Because it selects which molecules it wants to enter or not, right? Remember I told you the cell membrane is basically this border, right? This border agent that is checking to see what is coming in or not. So what enters and exits the cell is controlled by the cell membrane. We recognize this cell membrane, right? It's these phospholipids that are all together, right? This bilayer. And so this is why the cell, basically, sorry, some substances, they will pass through more easily than others. Look at this little picture here. Here's our cell membrane, right? And he says, "Excuse me, do you have an appointment?" And here's a little sodium that's charged, and they can't get in, right? They're getting booted out. So they can pass through the membrane. We'll see why that sodium can't get in. It has to do with its charge, that it has this positive charge. Oxygen over here says, "Yup, we have an appointment, let's go." And it just passes right through the membrane, right? So somehow these phospholipids, they're filtering whether some things come in or not. They're a selective barrier. Some things can go in, like this oxygen, and some things cannot, like this sodium. And this is why the cell membrane is called a selective barrier, but also it's oftentimes called a semi-permeable membrane. To be perméable in French, right, means to go through and penetrate through, such as imperméable means not permeable, like a raincoat, or an imperméable is what we call a raincoat in French, right? So what does semi-permeable mean? It means that some things can permeate through, some things can cross the membrane, but other things cannot cross the membrane, right? So which molecules freely cross the membrane? What passes easily through the membrane are these small molecules, right? If they're small, they can wiggle through this little membrane, right? And then here it says uncharged and nonpolar and hydrophobic. So I want us to remember what this membrane actually is, right? Over here, you see the little tails in the plasma membrane? These little tails are hydrophobic, right? Remember that they point inwards so that they don't touch the watery outside or the watery inside. So these tails are pointing inwards because they're hydrophobic. That's because they are non-polar. They're full of carbons and hydrogens that are non-polar bonds. And like dissolves like. Only the polar things will want to touch the water on the outside and the inside, and these tails flip inwards to hide from the water. So, what can pass through? Small things, of course, but also things that are not polar, right? If you pass through these tails, these hydrophobic tails, you need to be okay with mixing with hydrophobic things, with non-polar things, right? So if it's not charged, uncharged, and doesn't have like a plus or a minus, then it could probably get through, right? Because charges do not, they are polar, right? So they would not be able to interact with the hydrophobic tails. Nonpolar and hydrophobic molecules can also pass through because these tails are also hydrophobic, right? So whatever is hydrophobic and nonpolar can go through. Now, what does not pass easily, right? And these will need some help to pass by are large molecules, right? If they're big, then they'll need some help. If they're charged, they will um, also need some help because they will interact with these they will not like this hydrophobic inside, and um, anything polar or hydrophilic like water, right? Those will not be able to go in the middle because those tails are hydrophobic and they do not like things like water that is hydrophilic. Let me give you an example. It might help a little bit, okay? So first of all, what can pass through small, uncharged, nonpolar molecules. For example, O2. Let me go draw O2. Okay, I'll draw it up here. The O2 molecule looks like this, O and O. It has a double bond, who cares? So remember what we talked about O2, or even any molecule that binds with itself. This little arrow is going to pull this way, and this little arrow is going to pull this way. Is this going to be a polar bond or a non-polar bond? This is going to be non-polar because oxygens are twins, right? And they'll pull at the same strength. And so the electrons will stay in the center over here, right? And they won't be pulled more to one side or the other. There won't be a pole that is negative, right? This will not exist. And a pole that is positive, that won't exist, right? Because they're pulling equally, the negatives will stay in the middle. So that's called these O2 molecules, these are polar, right? Let me go show you CO2, right? CO2 looks like this over here. This is a CO2 molecule and it's linear, it's straight, okay? You don't need to know all this chemistry. I'm just showing it to you if it makes a bit more sense. CO2 is a small molecule, and look at this carbon-oxygen bond is indeed a polar bond, but it's pulling the electrons this way. And this CO bond is pulling the electrons this way, right? So all in all, look at these two forces. They end up canceling out because they're pulling on opposite ways, right? This would make CO2, that would be non-polar as well, because there's not one pole more than the other. They cancel each other out, okay? So you don't need to know the chemistry in detail, but I want you to know that these two molecules, O2 and CO2, they're non-polar, right? And because they're non-polar, they're not charged, they're small. These little tails here in the middle, right? These little tails that are um, uh, kind of hydrophobic in the middle, they will allow these other non-polar things to pass as well. Remember these tails, if I looked at them, they're full of these CH bonds. And remember that CH, that is a non-polar because C pulls the same amount as H. They're practically twins, right? So in this case, right, O2 and CO2, all I need you to know is that these molecules, they can penetrate through very easily. These respiratory gases could pass by easily. Another thing that could pass by easily is a bit of a bigger molecule, just a little bit bigger, such as a steroid hormone, right? If you go look at our lipid section, right? Steroid hormones are part of that lipid biomolecule. And lipids, we know that what is important about lipids is that they're hydrophobic, right? So these two things were hydrophobic, and this here, this steroid hormone is hydrophobic. So it too will be able to pass through this hydrophobic middle zone of the plasma membrane, right? So these little steroid hormones will be allowed to get through. All right. Now, next thing, right, is things that cannot go through. So these two things were uncharged, nonpolar. These were small and these were big, right? And so those are the types of things that could go through. The things that cannot go through alone without help are things like monosaccharides, right? Things like amino acids, right? Those two things are, those two things are going to be, look at them. These, we know that monosaccharides are full of OHs, which means they're polar, right? This amino acid is full of positives, negatives, O's, H's, N's, right? So this too is very polar. Um, Water is very polar as well, right? Because of those OHs. Just a little reminder, right? Water looks like this, right? And O pulls on the H and electrons, and O pulls on this H electrons, and there's these partial negatives and partial positives, right? All of these have OH bonds in them, right? And that's going to be making it polar. So they do not want to interact with this middle hydrophobic layer. Remember, water doesn't want to interact with oil, right? When you put oil drops in a water glass, they don't interact. So these very polar molecules do not want to interact with this middle zone over here. Now, um, the other thing that I didn't mention here was these sodium and potassium ions, right? Ions are charged elements, right? Remember we talked about when we form ionic bonds, we have these little charges. So over here we have sodium and potassium ions. They're little pluses. They will not want to interact with this hydrophobic inside, right? Um, very good. So lastly, large molecules like polypeptides, polysaccharides, nucleic acids. First of all, these are all polar as well, but they won't be able to go in because on top of it, they're very bulky and they're big, right? Um, all right. So let's talk now about concentration gradients, okay? So now we know that, certain things could pass freely through the membrane and other things can. But what is it that allows things to go through this membrane, right? And that's concentration gradients. Concentration gradients are unequal distributions of particles between two solutions or across a membrane. This thing here is like a pretend membrane that we have, let's say like your cell membrane, right? We're pretending it's like the cell membrane a little bit. And so um, when you have a concentration gradient, concentration means the amount, right? Like, for example, you could say I have concentrated coffee, right? In the same mug, right? You could have the same amount of coffee, but it could be filled with more water instead of coffee. That's a low concentration of coffee, right? Imagine these little molecules are caffeine, right? If you put not much water, then you'll have this very concentrated espresso on the left. And don't if you don't put much coffee and instead put a lot of water, then you'll have um, this very weak latte on the right. I love lattes, but anyway, this is on the right. You have a very dilute coffee, right? So, in other words, right, concentration gradients mean that there's a difference between a certain membrane. There's an unequal distribution of particles between the two solutions. So, for example, here we have a high gradient concentration, and I could write it like this. So I could write a very high concentration of solute, right, on this side. Remember, solutes are the things dissolved in the solvent. And here I have a very low concentration of solute on this side, right? That's a gradient. The difference between these two, the fact that there's a difference means that there's a gradient that's formed here. Okay, now molecules can move with or against their concentration gradient. So on the left here is the most likely scenario. Um, Molecules actually want to move down with their gradient. I forgot to explain to you what the word gradient means. Um, Sometimes we think of les cheveux gradés. It means that there's like a high amount at one end of the hair and then it gets a bit lower and lower, right? Like a gradient or a gradation is like a hill, right? You could say, oh, there's a steep gradient in this hill. That means it's a very high inclination, right? So moving down the concentration gradient means that you go from a very high elevation to a low one. But this is not a hill gradient, this is a concentration gradient. So it means that when you go down the gradient or with the gradient, you go from a high amount of solutes to down to this lower concentration of these solutes. So particles move from a high concentration to a low concentration. Okay, here there was a lot, and here there's not many. There's no energy required to do this. Molecules want to go from a high concentration to a low concentration. And we'll talk about this in a second, why that is. If you're doing the opposite, we say that you're moving up a gradient. You're moving up the hill, right? When you go from the lower ends of the hill to the higher ends, that's up a gradient. Or we call it against. You even know this. To go up a hill is much harder than going down, right? So you're going against the slope, right? So here you're going from low concentrations of solutes to high. Particles will move from a low concentration to a high concentration, and energy is required here. We're going to see this in a bit, okay? But I just want to get you used to the terms gradient and going up or down the gradient. Why is energy required? You even know this. To go up this hill is a lot of energy compared to going down it. You could just go down the gradient with the gradient, right? Okay. So let's keep going. So now I need to tell you what diffusion is, because now we have the proper vocabulary. So I talked about gradients, right? A difference in concentration somewhere. Well, diffusion is actually the fact that molecules, they have a natural tendency to diffuse with or down their concentration gradients, okay? They will Molecules naturally want to go from an area of high concentration to an area of low concentration. Take a look at, I want you to look at this picture over here. The red dots are all going to accumulate in this corner. And if you let them bounce around, right, then they will diffuse, right, and they will bounce around and equalize everywhere in this area, right? Um, Molecules, they have a natural tendency to bounce around because of the thermal energy, this Brownian motion. They have a natural tendency to bounce off each other, and they will spread out equally across this area. Okay? I want to give you a better example than this. Look at this coffee over here. Maybe not the exact video I wanted, but I want you to think about coffee, a cup of coffee, and you just pouring a little splash of milk in one corner of the coffee cup, right? If you pour it at the top in one corner and you let this go for a few seconds, this milk is not just going to stay there, right? The molecules are moving around and they diffuse around, right? You have this high concentration. Let me draw it maybe over here, right? You put this high concentration of milk here, right? And over time, it will diffuse to these lower concentrations that are a bit further away, right? So because of this diffusion, right, molecules tend to go from high to low concentration. I want to go back and remind you, this is our left situation, right? High concentration of milk in one corner of the coffee cup will want to diffuse across your coffee cup to the lower concentrations, right, that are everywhere in that cup. So that's what diffusion is. Even I like to think of like a diffuser, right? When you have a diffuser, you have concentrated perfume in it, and then all around your house, there's no perfume molecule. Why is it that those molecules move out into the air? Because that high concentration of perfume inside the perfume bottle will diffuse out into the air, right? That's what diffusion is. There's a natural tendency, no energy needed, for molecules to equal out. Take a look at this. Molecules, they're always bouncing around, right? And so over here, for some reason, these molecules here are at a high concentration on this side of the barrier. And on the other side of the barrier, there's none at all, okay? And what's going to happen if I if I just shoved all these molecules here, right? And then I allowed it to move around, then these molecules will bounce. Some will bounce back, right? But a lot of them will bounce through these little slits. And look how tightly packed they are. They're going to be bumping into each other and bumping and kind of pushing each other out the door, right? So molecules, there will be a net diffusion out into this lower concentration. Look over here at time, maybe give it 2 seconds, you have some molecules that ended up over here, right? And then there's still a high concentration here and low over here, but these molecules on the right are not bouncing into each other as much. And so these high molecules, high concentration, will keep bouncing over and go to the other side. And this will happen until you reach this equilibrium, until you have the same amount of molecules on each side. And this is called equilibrium, dynamic equilibrium, because molecules are still moving, right? Molecules don't just freeze when they're done. They keep bouncing around, and some will bounce off the walls, some will bounce and go back across, but at an equal level, since they're equal concentration, you have the same likelihood for these molecules to bounce back to the other side. So there's this equilibrium, there's an equal movement on both sides. There is no more gradient here, right? Here there was a gradient. There was a high gradient and it wanted to move down to the lower one. And then they were doing that. And then over here, there's no gradient, so there's no net movement, right? There's still some movement, like particles are going across, right? But there's no this net movement over here is zero because they're equally going on each side. I really like this analogy of the house party, okay? When you have a high concentration of people in this house, right? You're at a party and they're packing everybody in this house. There's disgusting, stinky people in this house that really didn't put deodorant on, and it's gross and people are throwing up everywhere. You are going to want to have this high concentration of people at the party. You will have the reflex to exit that house, right? This will require no energy. This girl saying, I just want to go home. And you will go onto the balcony where there's more air. You will go in your Uber where you're all alone with just you and the driver. So you go from this high concentration of people down to the low concentration of people in the Uber, right? And this is a natural tendency of ours to want to move away from this stinky environment. If you did the opposite and you forced your friend over into this crazy house party, right? You would need to use energy and push them in, right? So that would require some energy, right? But getting out this house is a very natural tendency, okay? So I hope that analogy made a bit of sense. Um, so over here, let's just go over a few terms we'll need now that we're talking about transport. We'll talk about how molecules are moved across the cell membrane. And there's two types of transport. There's passive transport and this active transport, okay? So let's start with our passive transport. No energy is needed to transport molecules from this high to low region. Let's say these molecules, right, this crazy packed house party, and outside there's less people, molecules will want to naturally go through. If they're allowed to pass through the membrane, they will naturally go from high to low. That's like going down the hill, right? Skiing down the hill from a high gradient to a low one. So you're going down the gradient, you're going from a high concentration to low. In active transport, right, energy is needed to transport molecules from a low to a high concentration. Here you have this very low concentration of molecules, right, on this side, and here's a very high one. But look at what this transporter is doing. This bridge is carrying these molecules to where it's packed. It's forcing these little solutes into a region where it's a lot of people in the house party. We don't want to naturally do this. This requires ATP. This requires energy to do that. This is why we talked about ATP for so long, because we need ATP to force things across where they don't want to be. And I'll tell you why that is in a bit. So think of the little biker, right? If you're going against the gradient from low concentration to high, you will require a lot of energy. You will require ATP to get you from low to high. So we're going to see these two types, this passive and active transport, in a minute. Um, Now, I want to just remind you that diffusion, this is a type of passive transport, right? Molecules want to do this. They want to go from high to low. They want to go from this high concentration down to their low concentration, right? But now we're going to see some examples also of active transport later on. So let's start with this passive transport. Look how this is organized. In molecular transport, you have passive and you have active, right? We're going to start with this passive transport, and in particular, we'll start with this simple one. So in simple diffusion, right? There's remember passive transport. I want you to remember no energy needed because we're going down the hill, right? We're going to see simple diffusion. We'll see facilitated and osmosis. Look at our little key over here. We have simple, facilitated, and osmosis. So, simple diffusion occurs when solutes can simply diffuse through. Occurs when solutes can pass freely through the permeable membrane, right? Solutes move from this high concentration to this lower concentration down their gradient. Remember, high to low, right, is a type of passive transport. You don't need energy, right? So, for instance, let's take a look at these lipids. There's a high amount of lipids, and here there's a low amount. Where if these, first of all, are lipids allowed to go through? Yes, right? Lipids are allowed to go through because they are hydrophobic and they can pass through these little tails. So lipids will, if they're allowed to, they will move down their gradient into the cell. Here is some O2. Remember I told you that oxygen was nonpolar? So oxygen is nonpolar and can easily pass through. It too will go from a high concentration gradient to low, right? Now, for some reason, CO2 is very high inside the cell and very low on the outside. Where will CO2 want to go? It'll want to go from high to low on the outside, right? This is still simple diffusion. This is still passive transport. Passive transport does not mean coming into the cell or going out of the cell. It just means going from wherever it's highest to wherever it's lowest, okay? So in this case, solutes are moving from their high to their low concentration, down their gradient. And remember, why does O2 and CO2 and lipids cross? Because they are nonpolar, they're hydrophobic, they're able to just pass through. I'll go back to this slide over here. Remember that these respiratory gases and these small hydrophobic molecules, they could just simply pass through, right? So what happens, right, in this case is that these things simply diffuse through because they're hydrophobic. Now, if I take over here a look at this, we did simple diffusion. Now we're looking at facilitated diffusion, right? This is still passive transport. No energy will be required, but I need some facilitation, right? This is basically, I need a bridge to go over, right? I need a little helper. Many small and charged particles, like over here, right? Imagine these being small and charged, right? Or these big, large, and polar molecules, imagine these glucoses with all their OHs, right? They are hydrophilic and they cannot pass freely through the plasma membrane. They cannot go this way because they're polar or they're charged, right? So instead, these molecules, they still want to diffuse down. They don't want to use any energy, right? They want to go down their gradient from high to low, but they just need a facilitator, right? They need facilitation. They need a membrane-bound protein, this protein over here, to allow them to go through. Why does this protein allow them to go through? Because the little amino acids in the inside here, right, are probably charged with pluses and minuses. These amino acids are polar and allow the molecules to go through, but these amino acids on the sides over here, right, are probably non-polar and allow them to sit in the membrane. So this is like a hole in the little protein, and these molecules can pass through and get to the other side, right? So now what's the difference between channels and carriers? In facilitated diffusion, you could go, these are just two types of bridges. Channels, right? Channel proteins, these proteins transport small molecules that are charged, such as ions, right? Sodium, potassium, chloride, all of these have charges, right? So they need a channel to go through. Or you could go through some things like to go through a carrier protein, right? These proteins transport large polar molecules like glucose and amino acids. Remember, they're much bigger and they're polar. They're going to go through these carriers that actually change their shape. It'll bind in, change its shape, and send it out on the other side, right? So that's facilitated diffusion. I want you to know that there exist various types of carriers and channels, and all depending on the types of solute they transport, right? They will be different, right? So they're very specific. That's the only thing I want you to know here. Carriers and channels, they're very specific. When a molecule is small in charge, right? Remember, it uses the channels. So an example of one, you don't need to know this example per se, but in this case, this ryanodine receptor, this is a channel protein in your muscle that just transports calcium ions. Doesn't transport potassium, sodium, only calcium, right? So it allows high concentration of calcium to go in to the lower concentration regions. When a molecule is large and polar, right, like glucose, then it'll use a carrier protein, right? So let's look at this example. The GLUT receptors, which stands for glucose transporters, right? They are a family of carriers transporting glucose down its gradient into the cell and without any energy, right? If glucose wants to go from high to low into the cell, it carries the glucose. So it's not going to carry amino acids. It's not going to carry calcium. It just carries glucose. So this is a way also for a cell to decide what comes into the cell or not. If it wants glucose to come in, it'll put a bunch of these glucose transporters on its membrane. If it doesn't, it'll take them off of its membrane, right? If you want people to come onto the island of Montreal, you're going to open up the bridge, right? If you don't, then you could block the bridge and say, please don't come in. So, which direction will the solute move, right? How many green solutes will be on either side of the membrane? I want you to pause and think about this. Okay, so in this case, right, let me get my green out. In this case, we have a high concentration of solutes here. 1, 2, 3, 4, 5, 6, 7, right? So I have 7 versus 3 solutes, right? And so the high concentration, right, of solutes is high over here, and it's very low concentration of solutes over here, right? It's very low. So things will want to move this way in this little carrier, right? Let's pretend this carrier can actually carry it over, okay? So in this case, one of these little molecules will go in the carrier and cross over. So all of a sudden, I'm going to have 1, 2, 3, 4. And I'm going to have 1, 2, 3, 4, 5, 6. Right? Oops. Let me just go back. This is a circle here. So I've brought this over to the other side and transported it here, right? So now all of a sudden, let me just erase this here. Right, now I've transported one over. And so let's go back and count how many we have. We have 1, 2, 3, 4, 5, 6. 6 versus 1, 2, 3, 4. 4, right? Now I'm going to take one of these and transport them over to this side, right? 1, 2, 3, 4. So now I'm going to have 5 on this side, and this one will go away, right? Because it got transported over. So let me erase this one, okay? And so now if I do my count, right, I will count 1, 2, 3, 4, 5 on this side, 1, 2, 3, 4, 5 on this side. They're equal. Now I've all of a sudden reached equilibrium. Is there a gradient still over here? No, they're equal, right? There's not going to be any gradient in this case, so nothing will move, right? They're going to stay equally on both sides. So that was an example of facilitated. So either you simply diffuse through, or you use a facilitator to help you go through, right? But both of these have no energy required. Now, osmosis is the next one in line, okay? Osmosis is basically facilitated diffusion, but for a special molecule called water, right? So solvents like water molecules also cross the cell membrane, and these polar molecules need facilitation, they need help via a special channel protein that we call an aquaporin. This is an aquaporin over here, okay? And water molecules, right? These little water molecules will want to go from and move down their gradient as well, right? So here you have high amounts of water and they will move to this lower region over here, right? Water also moves down. So that's a type of facilitated diffusion. It's called osmosis. Now, water is a little special though, because water can help us with different gradients, okay? So, for instance, some solutes in cells move across the membrane while others can't, right? So, water, on the other hand, can always move across the membrane with the help of aquaporins. So, in diffusion, for instance, right, here I had these green little molecules. Pretend this is a cell membrane, and this is a high concentration and a low concentration. In diffusion, we saw that a solute, like this green solute, is penetrable. They're able to cross the membrane and they'll move down their gradient, right? So over time, if you let time go by, this penetrable, permeable membrane, right, will allow an equal balance of both the solutes on each side. Now, in osmosis, when a solute is non-penetrable, let's say these purple solutes cannot cross the membrane. Here I have many solutes, and here I have 1, 2, 3 on this side, right? Let's say that this membrane does not allow the solutes to move, right? Well, water is a good friend, and it will move down its gradient, right? So here I have a very high solute concentration, right? And that would mean that I have a low concentration of water, right? Here I have a very low concentration of solute, and I have a very high concentration of solvent, of water, right? So where over here in this case, this membrane is semi-permeable, it only allows water to go through. So water will move from its high concentration to its lower concentration. It'll move this way. That's osmosis. But look at what it does. In doing so, it actually helped out to balance out the solutes, right? Look at pretend that this is a coffee here, right? With this specific volume, high in caffeine, this would taste very bitter, right? And this coffee over here on the right doesn't have many caffeine molecules in it. It would taste pretty dilute, right? Well, water is going to move out of your very diluted coffee into the region that's more concentrated, and it will change the volumes, right? The solvent moves down its gradient, right? I like to think of it as water moves towards the high concentration of solute to go and dilute it. Water's moving this way to go and dilute this very high concentration of solute that cannot go through the membrane. So water moves to the left, right, as time goes on, and water will actually go and dilute these over here. If you tasted this coffee versus this one, yes, there's less of it over here and more of it here, but they would taste the same. Look at the concentration of purple particles. They're equally spread out here and over here, right? because water went to solve the difference in concentration. Take a look over here. Here I have these sugar molecules on this side, right? And I have water on both sides, okay? Now, water is a lot more concentrated on the left and a lot less concentrated on the right because of those sugar molecules, right? So water will want to move down its gradient and across, right? But also, sugar here is huge, right? It cannot go through this membrane. If sugar could go through the membrane, right? It actually would. Sugar would want to move where? It would want to move from this area here down this way, right? But it can't. This sugar is too big to pass through. Therefore, instead, water will move through the process of osmosis, and water will go to the higher concentration of sugar so that it could dilute that area, right? So that's what osmosis is. Now, why is this important to us, right? If we place a cell in solutions of varying solute concentrations, how will the movement of water across the membrane affect the cell? This is called tonicity, right? The ability of an extracellular solution to make water move into or out of a cell by osmosis is known as tonicity. Whoa, what does this mean? Here I have a little cell, and all our cells have a certain amount of solutes. Here I have a solution that this red blood cell is floating in. This is like our blood, right? Blood is a bunch of water and red blood cells. So the plasma, the water outside the cell, is over here, and the red blood cell is over here, and each of them have a certain concentration, right? And if they have different concentrations, right, they will allow water to move in and out, right? They will have a different tonicity, we say. So a hypotonic solution, remember the solution is the outside part, right? So the hypotonic solution, in this case, right, in this beaker, we have this this lower tonicity, we have this lower amount of particles on the outside of the cell, the solution, compared to the inside. So the solution that these red blood cells are in has less solute than the cell, right? If it's iso means the same, right? Like in an isosceles triangle, you have two of the same sides, right? Iso means the same. We're going to see this word a lot this semester. Isotonic means that the outside solution is the same as the inside. Let's count the solutes. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? 5 versus 5, that means that they're isotonic. They have the same tonicity. Hypertonic, right, solutions means that the solution on the outside has more solute than the cell on the inside of the cell, right? So let's see here. 1, 2, 3, 4, 5, 6, 7, 8, right? Versus 2 on the inside. This is a hypertonic solution compared to the inside. Now, if you watch Grey's Anatomy or something, you might hear the doctors and the nurses screaming, "Oh, get me a hypertonic saline solution for this patient," right? When you give an IV to a patient, right? You cannot give them pure water. When you want to hydrate a patient, you do not put pure water. You actually put a saline solution, which is full of solutes, right? And this is because exactly this thing, red blood cells have a certain amount of solutes inside. If you go dilute the outside, right, you're actually going to end up dehydrating your patient, okay? And we're going to see how this could be in a minute. I want you to take a minute and do this little exercise here, okay? All right, so how do the solutions A, B, and C relate to each other in terms of tonicity? I guess I put this little problem here to emphasize that it's not necessarily that, how can I say it? It's not necessarily that a solution is hypertonic or a solution is isotonic. You cannot claim that something is hyper or hypo. You need to compare it to something else, right? Like over here, we compared it. We said it was a hypotonic solution because we compared it to the inside of the red blood cell, right? So over here, right, when you're comparing A and B, you're going to say A is less than B, right? And less than hypo, lower, right? When A is less than B, we say that this is this hypotonic, right? It's lower. So A is hypotonic compared to B. A is more compared to C, right? So A is actually hypertonic, right? Compared to C. C has absolutely no solutes, right? So that would be A is hypertonic to C. Now, B, right? Let's go to our B. B compared to C, B is hypertonic compared to C because it has more, right? So hypertonic. And B compared to A, B has a lot more compared to A, right? So B is also hypertonic compared to A. I hope this shows you that it depends what you're comparing. You could say A is hypotonic to B, or you could say B is hypertonic to A, right? So those are the vocabulary words that we'll be using a lot. Now, a cell is hypotonic in a hypotonic solution when a cell is placed in a solution containing less solutes than we find inside the cell, right? Here, this solution is a hypotonic solution because there's a lot less of those solutes on the outside compared to the inside, right? 1, 2, 3 versus about 6, 7 in here, right? And so if we have less solutes on the outside, right? If the solutes could move, right? It'll travel down its gradient. The solutes would move from high to low. Let's say they did have a transporter. They would move from high to low and they would balance out if they can. But if they can't, right? If a solute cannot pass through the membrane and they don't have a transporter, right? And they're impermeable, these solutes, right? Imperméable means not let through. If these solutes cannot get through, right? Osmosis occurs and water, the solvent, will move instead, right? In this case, right? Let's go and take a look at this. Here I have high solutes inside, low on the outside. They can't move. We're told that they cannot move through the membrane. And so water will flow into the cell, right? To go and dilute this high concentration of solute inside and leave the lower concentration on the outside, right? In a sense, water's concentration gradient, if I went to talk about water, water is at a high concentration, right? Water is high on the outside, and water on the inside is all crammed in here. It's a low concentration of water, H2O, on the inside, right? So it'll want to move from outside to inside, right? And if these are red blood cells are quite fragile, right? And so water, if it keeps coming in, eventually it could reach a scenario that's called lysing or bursting, right? If too much water, think of a water balloon, eventually they burst, right? So hypotonic cells, right? When cells are placed in hypotonic solutions, they swell like a hippopotamus, right? You don't need to memorize it. You need to understand why it is. A hypotonic solution has less solutes outside, so water wants to go in to dilute it, right? Look at these red blood cells. This is a true micrograph of them. Usually red blood cells are disc-shaped, okay, we're going to see a normal one. These are bursting, they're spherical, and they're about to bust, right? Let's look at hypertonic. When a cell is placed in a solution containing more solutes than we find on the inside, right? This is called a hypertonic solution. And the solute will travel down its gradient into the cell. If it could, if these solutes, these purple little dots could, they would move from the outside into the cell, right? But if they cannot, right? If a solute cannot pass through the membrane and it's impermeable, then osmosis will occur, right? And so what happens, right? The water, that solvent will move instead. So in this case, you see that water will go from this inside, right, where it's highly concentrated, and it'll move outside where water is low concentration, right? And so water flows out the cell to dilute the concentration of solute on the outside of the cell, and this will cause shrinking of the cell. This is called shriveling or crenation, right? So look at these cells here. These are real red blood cells that are in hypertonic solutions. They have all these little blips on the side because they're kind of shriveling up like a grape. So hypertonic cells, they dehydrate like a hyperkid. I guess that makes sense. So hypertonic, right, means that they're in this hypertonic solution. They'll dehydrate like the hyperkid. Now, isotonic solutions, when placed in a solution whose solute concentrations match those of inside. Let's count. 1, 2, 3, 4, 5, 6. 6 on the outside, 6 on the inside. Then this is called an isotonic solution, and there's no net water movement. Some water comes in, and some water equally comes out, right? It's a net zero. There's no net movement of water. Solutes and solvents are at what we call dynamic equilibrium. They're moving back and forth, but there's no net change in the concentration, right? So cells maintain homeostasis by maintaining the concentrations of solutes in and out of the cell to ensure that the net movement of water is zero, right? So we actually want to be in these isotonic solutions. Isotonic solutions in humans are not zero solutes. Our insides of our red blood cells do have some saline in it. They have some salt like sodium chloride, and that's why when we give an IV solution, we do put a certain percentage of salt in the IV bag because we actually want to match the inside of the red blood cells. All right, I hope that makes sense. Now, just a recap, passive transport, all of these were no energy required, right? In simple diffusion, things simply move down their gradient. In facilitated diffusion, things move down their gradient, but with a facilitator, a helper, bridge. In osmosis, water moved down its gradient, so it didn't need energy. But now we're moving on to active transport. And in this case, energy is required, okay? So we're going to see that there's primary and secondary active transport. Why did we talk about ATP, all of these classes? Because active transport requires energy. It requires ATP. Remember, this is our payer of the cell, the dollar bill of the cell. And there exists two types of active transport that require ATP, since molecules are transported against the gradient, right? ATP, all these diffusions that we saw in the passive transport, right? They were going down the hill. But active transport actually is going up the hill and requires some energy, right? We need ATP. So primary active transport actually is driven directly by ATP. Secondary active transport is driven by a gradient. The primary transport helps to transport in the secondary step. So take a look at this. Here, primary active transport directly driven by energy source, ATP hydrolysis. Here, there's a little bridge to get over, right? And ATP is used over here and pays the little bridge to send a molecule over from a low concentration inside to a high concentration on the outside, right? And here, once we generate that high amount of concentration, then that high amount will go down its gradient, but it'll carry another molecule, right, down their gradient. So it'll help another molecule go down. I'm going to show you what that is in a minute. Let's start by primary active transport. So what is primary active transport? It carries solute molecules against or up their gradient from low to high. So we're going from this low concentration to high. Look at this transporter. Low to high. We're shoving it across into the house party where it doesn't want to be, right? It generates important solute concentration gradients that are going to be essential for cell survival. We'll see why is it that it's doing this? Why is it shoving things where they don't want to be? There's a very important reason, and we'll see it in a minute, okay? So, this process, right, I want you to remember that it's directly driven by energy derived from ATP hydrolysis breakdown. So you take ATP and you hydrolyze it, you cut off the phosphate and you put it on this molecule, you pay with an ATP molecule, right? So remember, this is active transport. We need energy, right? And we use a carrier membrane protein. We're not going to call it a carrier now. We actually call it a pump. Why is that? Because it's pumping things from a low concentration to a high concentration. Think of a pump. This guy is a pump in a sense, right? Here you have high amounts of water, right? And in the boat, there's a low amount of water. And water wants to move into the hole, right? Into the boat in this lower environment. But this guy is pumping out the water from low to high, right? So he is a pump because he's continuously pumping things where the water where it doesn't want to be. Or think of just of a regular pump, right? When you have a flood, right? There's a high amount of water in your basement maybe, right? And you put a pump in your basement and you shove a hose outside and you're pushing the high amount of water in your basement out and you're pumping it outside where there's less water, right? So that's what a pump is. It's moving things against their gradient. It's like a carrier, but for active transport. So how is ATP hydrolysis used in primary active transport? It's ATP hydrolysis, this exergonic reaction, right? It transfers a phosphate. It breaks off one of the phosphates into ADP and phosphate, right? And this phosphate gets tagged onto the membrane protein. Remember, this phosphate is negatively charged, right? So look at these yellow molecules binding into the the pump, right? These three yellow molecules here, right, will be pushed to this higher concentration on the outside, right? Because this negative phosphate changes the shape of this carrier protein, right? This pump gets shifted in its shape, right? And the energy from this phosphate changes the shape of this molecule to shove them onto the other side, right? So it changes the shape of the pump ions so that they go against their gradient, which that is an endergonic reaction, right? So we're using it to do work in the cell, right? The transfer of energy helps perform work that wouldn't otherwise be done. These yellow molecules do not want to go on this side, but this pump uses ATP breakdown to shove them to the other side. So, an example of primary active transport, why is it important? Well, because in our bodies we have the sodium-potassium pump, okay? The sodium-potassium pump, ion pump, right, is one of the most important in the cells since they must maintain a high concentration of sodium on the outside and a high concentration on the inside. The truth is, our cells for some reason, they always keep this high sodium on the outside and a high potassium on the inside. There's a very important reason why. We're not going to talk about it now, but this sodium potassium pump is an example of primary active transport. Here, right, you see that this pump moves sodium and potassium against their concentration gradient. This is active transport. They're not going down their gradient. ATP is used to shove 3 sodium ions out of the cell, right? Look, all these sodiums that are normally in the cell, they get shifted out and chucked out to the outside of the cell, right? And it actually uses ATP to do this, right? It breaks down ATP into ADP, it puts its phosphate, and sodium is shoved from low to high. At the same time, this channel will shove 2 potassium ions into the cell. These 2 potassiums there's many potassiums on the outside. They will shove these 2 into the cell from low to high, right? So for the sodium potassium pump, I want you to know this example because it's going to come up in the nervous system. A little maybe Halloween-y trick. The pump, it pumps K plus in, right? Like a pumpkin pumps K plus into the cell, right? And sodium out of the cell. So an example of this, right? This is the same example. I'm just showing it to you in a different way. Energy is used to move sodium ions and potassium ions against their gradient. If you want to add it yourself, I want you to put a bunch of sodiums, many sodiums on the outside over here. And I want you to put many potassiums on the inside here, right? Because here it says sodium is high on the outside and potassium is high on the inside, right? This is the outside of the cell. This is the inside. So how this works, cytoplasmic sodium binds to the sodium potassium pumps. 3 sodiums bind over here, right? Sodium binding stimulates phosphorylation by ATP of this pump. And so ATP comes and phosphorylates this protein. And phosphorylation causes the protein to change its shape. And sodium is expelled out, right? Then potassium binds on the extracellular side, triggering the release of this phosphate. And then potassium gets shoved into the cell, right, where it's very high. So this happens over and over, and this pump is constantly pumping things against their gradient. This is maybe a bit more of a better visual, right? Here's a cytosol inside the cell, right? You're bringing 2 potassiums in, 3 sodiums are going to go to the extracellular, and then you kick off an ATP, right? For every cycle of 3 sodiums and 2 potassiums, you use up 1 ATP. Can you imagine this? We're using energy to pump things to where they don't want to be. And there's a reason for this. Oh, not yet. We're going to go take a look at this example first, right? I want you to pause the video and take a look at this image where we have the sodium potassium pump, right? How many sodium and potassium ions will be on either side of the membrane after transport? And how many ATP are used? So pause the video. And so over here, right, we have this sodium in green, right? And we're going to take, because we know that sodium's in green because over here, so basically what we're going to do, right, we're going to take this sodium and we're going to take 3 of them and shove them across the membrane, right? So all of a sudden, I'm going to go from having 3 here, 1, 2, 3, right? Here I'm going to have 1, 2, 3, 4, 5, 6, 7, right? And so I'm going to shove 3 of them on the other side. It's going to be 1, 2, 3, and I'm going to get rid of 1, 2, 3. All right. So let me erase these now that we shoved them over. And at the same time, remember that I'm going to be using over here, I'm going to shove 2 of these into the cell. So I'm going to have already 2, right? And then I'm going to add 2 more. And then here I'm going to be ended up with 2 of them. Okay. So I want us to count now, right? I've just shoved a bunch of these sodiums outside, right? And now I could keep going. I have enough molecules to go around one more shot, right? So let me erase this. What I'm gonna do, right, is take three more. So sorry, I'm gonna keep track. That was one ATP to do those two things, right? Now I'm gonna take 1, 2, 3 and shove them outside, and I'll take these two and I'll shove them on this side, right? So let me go and put 1, 2, 3 on this side. I'm gonna put 1, 2 on this side, right? Now let me erase what I took away. Here we go. And now I've used up one more ATP, right? So all in all, this is what you'd be left with. I don't have any more sodiums. I need 3 sodiums, right? So I wouldn't be able to go again. But I've shifted over, right, all of these sodiums here, all the potassiums here, and I've used up 1 and 2 ATPs, right? So now we're going to talk about secondary transport. You know, I asked you, why does the cell do this, right? Like, what is the point of shoving things where they don't want to be? Well, sometimes when you create a gradient, right, we call this the electrochemical gradient. It's an imbalance of electrical charge and concentration across a cell membrane. When you have differences in concentration across a membrane or charges across a membrane, right, this has power to do work. So this imbalance can be thought as the potential energy, like water behind this dam, right, that's used to go against it goes down its gravitational potential, turns a turbine, and actually makes energy. Like, it makes work, right? It uses this specific energy. So this is an example, right, of how you could use a gradient. So let's talk about what is secondary active transport. First of all, primary active transport uses ATP hydrolysis to create the concentration gradient. Remember, we took a bunch of these sodiums and shoved them to the other side to make a high sodium gradient, right? That took energy, that took ATP, right? So now, right, now we could go and use that gradient to power our secondary active transport. So let's go through the steps of, for example, carrying sodium glucose through secondary active transport. Number 1, ATP pump, right, transport sodium against its gradient using primary active transport. Here I'm using primary active transport to shove sodium on this side, right, against its gradient using ATP. The higher concentration of sodium is generated outside the cell, and glucose has a higher concentration inside the cell, right? Like, sometimes, in some cases, some transporters want to shove glucose into the body. Like, we are constantly needing glucose. So even if we have high glucose in the body, our body doesn't want to waste glucose. It wants to shove it in the body. So in this case, we generated a gradient of sodium, and it'll carry, sodium wants to go down its gradient from high to low. And at the same time, it powers glucose to go against its gradient at the same time. It kind of drags it with it, right? So that it goes against its gradient. So in this case, the image below represents a sodium glucose pump. When the pumps bring 2 sodium down its gradient, it brings 1 glucose up its gradient, right? So how many glucose molecules will be able to enter the cell, right? In this case, right, we have, this is just saying that this pump brings 2 sodiums down its gradient, and it brings 1 glucose up its gradient, right? So it carries, we don't have a primary active transporter here. It carries 2 of them down here, right? And it'll carry 1 glucose this way. So let's first tally how many we had. We had 1, 2, 3, 4, 5, 6, 7. 7 of these little sodiums, right? And here I had 3 sodiums, okay? And now for the glucoses, right, I have 3, and glucose is here. I have 0, right? And now I'm bringing them over. So now I'm going to have 1 glucose on this side, and I'm going to have 2 on this side because I subtracted, right? And then I'm bringing these 2 over on this side, right? And so that's going to cost me, as I bring those 2 over, right? I'm going to go down from 7, 6, 5. This is going to turn to 5. And this is going to turn 3, 4, 5, right? I'm going to get 5 and 5. So if I were to redraw this now, let's get rid of these. I'll just put X's through them. And I'm going to draw 2 of these on this side. And I'm going to draw, let me erase these. And now I'm going to draw a little glucose here, right? Now, if I were to go again, right, you'd be tempted. We still have some sodiums on this side, but I want you to realize this is a secondary active transporter, right? I have 5 sodiums and 5 sodiums. Is there a gradient? There's no more gradient. So unless I had a primary active transporter that would use ATP, right, to go and bring these over, then I can't actually continue this pump, right? This is just the secondary active transporter. We didn't talk about the primary one. So in this case, I would need to stop here because I don't have any more gradient. The reason why glucose went down was because the green molecules, the sodiums, had a gradient, right? But now it's 5 and 5. There isn't any gradient to bring it down, okay? So for membrane transport, right? So we've seen passive, we've seen active transport. This bulk transport, it's actually a form of active transport as well. So I know here it says bulk. You could add active on the top over here because it does require ATP. It's just that it's its separate thing because it's a little bit weirder. Bulk vesicular transport means that we bring things over in bulk through vesicles. Vesicles, if you remember, they're little vehicles, right, that little molecules could be in, right? So we saw that small molecules cross the cell membrane or use membrane proteins, but very large molecules like polysaccharides or proteins, they'll cross the membrane via bulk vesicular transport. And how do they do this? They change the shape of the cell membrane to engulf or to expel things. So in this case, we call this endocytosis. Endo means into, inside. Cytosis means cell. So we are pushing the plasma membrane down and we cause this little dip, right, that will bleb off and form a little vesicle. This is called endocytosis. This is how molecules enter the cell. This costs ATP, by the way, active transport. And we're going to see 3 kinds. We're going to see phagocytosis, pinocytosis, and receptor-mediated endocytosis. Also, molecules could exocytose. They could exit the cell, right, and get secreted out if you want to send things away. So this is exocytosis. Also costs ATP to bleb in with the membrane and go outside, okay? So over here, right, let's see, here are the really 4 types. You have endocytosis here, these 3 types, and you have this exocytosis here. So in endocytosis, there's 3 subtypes. The first one is called phagocytosis, right? Remember, endocytosis means to bring in, while phagocytosis is bringing in large, solid material taken in by an this endocytosis. This is also called cellular eating, okay? Phago means to eat, right? So it's the cell membrane changes its shape. Here you see some food stuff outside, and the cell membrane changes its shape and blebs inside, and there's this little food vesicle here, right? So The cell membrane changes its shape to engulf damaged cells. Or also, so here, sometimes you want to break pieces off cells, or here you see this white blood cell that's chasing a little bacteria and eventually catches it, right? Immune cells commonly perform phagocytosis to remove infectious microbes from our body. There we go, he got it. These infectious microbes, right, they form uh, they're in our blood and connective tissue, and they patrol for bad little things, right? Here you'll see that I said we could phagocytose cells, microbes, dust, or ink. Actually, the reason why your tattoo will stay colored-ish, right, is because macrophages, these white blood cells in your skin, they will phagocytose the ink and they permanently stay in these white blood cells and they'll be colorful. This is a real tattoo when you see this macrophage that is nice and glistening with this green dye. Pinocytosis is this phagocytosis was cellular eating. Pinocytosis is cellular drinking. So small liquid materials taken in by endocytosis. So for example, the cell membrane changes its shape and engulfs water. It could engulf ions or other solutes, right? Little things and water to bring it into the cell. So this is a little pinocytic vesicle with some solutes that it's bringing in. This is not directed in any way, right? And the cell simply picks up what's immediately in its vicinity. So I like to think of cell drinking. Pinocytosis sounds like Pinot Grigio. So you have a nice little white bottle of wine over here to remember pinocytosis. And the third one in endocytosis is receptor-mediated endocytosis. So sometimes this is kind of like the two others, but this time specific form of pinocytosis uses receptor proteins. So this is like one specific molecule. These purple molecules really want to get in, and they bind to these special receptors that'll bring them in, right? So for example, this mechanism is used to take in certain lipids. Let's say these purple lipids, right, that don't cross the membrane very easily if they're too big, right? As these lipids are carried in very big body of large protein complexes, they could go and bind to these receptors, and then they could get pushed in, right, with a vesicle coat. When appropriate molecules bind on receptors, the section of the membrane is pulled into the cell. You see here the coated pit, right? They will bind and then they will bleb into the cell, right? So there's a receptor and molecule interaction here, all right? And lastly, there is exocytosis. If we would like to leave the cell, right, then we have what we call vesicular fusion with a membrane. So here are some green molecules that want to be expulsed, right? And so you see that this vesicle merges with the cell membrane, opens it up, and shoves everything outside. For example, that's how many cells secrete their products, right? For example, the cells of our sweat glands and pancreas, they'll make a bunch of these molecules of sweat, right? And they'll just push them out and exocytose, right? So that's glands often do this. So that was all for membrane transport. That was heavy, right? But review this little chart and it'll help you out a lot. Last few things, macromolecules of the cell membrane and maintaining homeostasis. So I just want you to know that, remember we talked about these proteins that are sometimes in the cell membranes? Well, sometimes we have some that are called integral membrane proteins because they are permanently integrated into the plasma membrane, and they usually span the entire bilayer. They're from one end on the outside to the inside. Other proteins on the periphery, we call them peripheral membrane proteins, just on one side. They're on the perimeter of the cell, right? Just on one side, the inside or just the outside, and they're kind of just laying there to communicate. So let's start with the integral membrane proteins. These over here that span the membrane. Um, we've examined some of them, many of them, channels and carriers, right? We've talked about these. Those are integral membrane proteins. But there exist many other types, such as receptors. Like sometimes there'll be a little signal that binds here and tells the cell to do something inside, right? That's called a receptor. You just saw a receptor over here, right? These were receptors that told the membrane to fuse inwards, right? So that's some examples of those. Also, you have sometimes they're enzymes on the cell membrane. You could have enzymes that convert certain reactants to products. And sometimes they're anchors. Sometimes these proteins are there to anchor to another cell or to another piece of tissue, right? That's called an anchoring protein. So, just a little, so that was integral proteins, right? These purple ones. Now these yellow peripheral proteins, right? What are peripheral membrane proteins? These peripheral membrane proteins, look at these G proteins over here, right? They are temporarily associated with the integral membrane protein. In green here, you see an integral membrane protein across the membrane, and the peripheral membrane proteins just on one side, right? Well, they form these non-covalent interactions like hydrogen bonds, right? The hydrogen bond, which means they could easily detach, right? And when a signal, like a receptor, right, comes and sits on the integral membrane protein, right, then this G protein will change its shape and go and unleash a bunch of receptors and actually go and signal inside the cell that maybe insulin got bound and that it should do something about it. Or maybe it'll go signal that, I don't know, it's the temperature is getting hot, so you must secrete sweat, right? So the peripheral membrane proteins easily separate from the membrane and play a role in transmitting information received from external signals. So last thing, we also have what we call glycoproteins and glycolipids. Think about it. So we know that there's membrane proteins in blue, right? We know that there's phospholipids in yellow and gray here, right? We know that there's cholesterol in orange, but now there are glycoproteins and glycolipids. They're crucial for cell-to-cell communication and to help the immune cells identify what is self and non-self. So look at the glycoproteins. Glyco, because there's a gluco chain, there's these carbohydrate chains, and protein, glycoprotein. There's the glucose part and the protein part, right? Biomolecules are allowed to mix. I know that we were very strict in saying there's 4 biomolecules, but sometimes they bind together, right? That's a glycoprotein. Here you have a glycolipid, a lipid with a little glyco chain coming out of it. So I said that these were for communication and so that the immune cells could identify which cells are yours, right? This is like a little name tag for the cell that says, I'm allowed to be in this body. I belong to your body. Because white blood cells actually will go and eat any cell that doesn't have a name tag on it. If there's no name tag saying this is Sam's cell, then they will eat it. That's good, right? Like a bacteria, let's say, that doesn't have my name tag on it, the white blood cells will be able to eat it. So why is it important that cells recognize self cells? Because in organ donation and rejection, right? That's how we make sure we're compatible with the organ that's coming into us. During infections, you want the white blood cells to go eat these things. During cancers, your white blood cells actually start mistaking things and start going out of whack and things that aren't there go crazy. During transfusions, right, these little carbs are what say I'm an A group or I'm a B group, right? So that's very important as recognizing an A, B, or O type of cell. We're going to see that when we get to the heart next semester. So last part is maintaining homeostasis. What is the fluid mosaic model? The nature of the cell membrane is like a fluid mosaic, okay? It is fluid because of interactions between phospholipids and cholesterol. So it's fluid because you have, this moving around, and it could really go back and forth. But it's a mosaic because you have a variety, like a mosaic of proteins, glycoproteins, glycolipids embedded in the membrane, right? So we actually call it the fluid mosaic model because there's a bunch of different types of these proteins that are all fluid around in this cell. And fluidity can impact diffusion across the membrane, right? Like, why is it that all of this lecture was important? If a membrane's fluidity, is changed, then it'll have big ramifications. A membrane's fluidity influences how easily nonpolar compounds could pass through, right? Those little gases, O2 and CO2, could go back and forth between cells, right? And so it'll impact how embedded macromolecules move around it. These little proteins around it, right? If it's too rigid and cold, right, and not fluid, then they're not going to really move around and do their job. Fluidity will influence the diffusion coefficient, meaning the speed that these molecules go back and forth between the membrane. And changes in fluidity impact homeostasis, right? For example, respiratory gases need to diffuse across at a certain speed to keep your tissues active. So I think that's all for this lecture, right? Make sure you do the practice problems that I put in the PowerPoint, and you'll be all set. And you can come ask if there's any questions at all.